Hey there, you 12s. In this video here, I'm going to focus on just the transformation section of exercise 15D. Just this box here that I had in my notes. And I felt like in the class I didn't explain this too well, why it was confusing. What I'm trying to say is that in a continuous random variable, you have a function. So let's just say a straight line, just to make the picture easier to see. Let's say that's your function. A probability density function means the area under the curve has to represent probability, and so we know it sums to 1, right? Then what we say is, okay, let's say it sums to 1 between 0 and 2, as an example. I'm just making it up right now. And what I want is what happens, because that's the variable x, that's a random variable x, right? What if I shifted, let's hypothetically just say for every x random variable I had, I added 1. What will then happen is this. You would actually then shift this box to the right by 1. I'm just going to do something like that. So it shifts across by 1. So from 0, it moves across to 1, and then from 2, it moves across to 3. Okay? And the area is still 1, but now the domains have changed. But what I want you to realize here is what's different and why it's confusing is that when I wrote f of ax plus b, what I'm really just trying to say is that the transformation that we want for the function is as it is described here. So when I say plus 1 before, I'm actually taking every x value and I'm adding 1 to it. And that's different to what you're used to seeing, which you might be seeing something like this. So for example, f of x equals x squared. And then I say f of x plus 1. That is equivalent to you substituting this into that x, and then that becomes x plus 1 squared, right? But then if you actually look at the graph for this one, so the quadratic is normally like this. That's your x squared. But then x plus 1 has a turning point at minus 1. You see that? So in fact, it's gone left 1 and not right 1. So why is it different in this scenario when I say f of x plus 1, it actually ends up being to the right 1, to the left 1. But in this scenario, we are now saying it is going to be to the right 1. And it's more on a conceptual difference here. Conceptually, I'm just saying this is the transformation that I want to apply to it. If anything, another way to sort of picture it is I'm saying for every x, y coordinate, I want it to now be ax plus b, and well, the dilation has to be 1a to keep the area the same. Because if I'm stretching it from a horizontal compression point of view, then I need to do a vertical stretch in the opposite direction to make it still the same. Otherwise, the area would be 1. Okay, so that's why we have that little extra note there, which is what I wrote over here. So note that you have the dilation of factor 1 and a from the x-axis to counterbalance that a dilation factor a there. Okay, so what I'm trying to say is this: when you read this part of the notes that I wrote, don't confuse this with what you're familiar with, which is over here. They're different, okay? And so to illustrate the concept is I want you to interpret it this way. This is what we're actually saying. So we're actually saying the transformation, you can actually read it directly from the actual thing that you want, because you want to move all the x values to the right or you want to move it to the left. You actually directly affect the x coordinate. So technically, your x transformation is based on ax plus b, and this is your direct transformation to get to your new y coordinate, which is y divided by a. Okay, and that's what I tried to show is in a proof in this new set of notes for you to understand. So let's say y is equal to f of x. That's your function, no matter what the curve is. The transformation we want is this. This is what we want, right? So for that transformation, when we say f a plus b, what we're actually saying is I want this transformation for the function. That's all I'm saying. I'm not saying I'm substituting ax plus b, and maybe that's where the confusion is, okay? So when I say I want this transformation, the question is, what am I substituting into to get the rule? This is the rule. That's what you're substituting in. That's the thing that you're substituting. So where did this come from? And where did this come from? Well, let's see where it comes from. So if you want to know the rule for the transformation, so this is your original function, and you want to know where the new function is going to be, okay, then we do exactly what we did in the chapter for transformation. We say, well, this is your x dash, this is your y dash, and you simply say, okay, well, x dash is equal to ax plus b. In order to figure out what the new equation is, remember it's y equals f of x, right? I need original x to replace, and I need original y to replace. So that's why I rearrange everything from this step. I say, okay, minus b on both sides so that I can focus on getting the original x. And then I say here, divide by a and divide this by a. The a's cancel out. And so original x will equal to x dash minus b on a, right? And then the other side is y dash. So our y dash over here is original y divided by a. Remember, you have to have the divide a so that the area stays the same. So if I find original y, I need to times a on both sides. A's cancel out. And you get a y dash equals y, right? So now what you do is you then say, well, this is original y, so I'm going to replace the original y function. And then this is original x, so I'm going to replace the original x. And that's what you end up substituting into the function, what you're familiar with, right? And so that's how I got that. So original x was equal to x dash minus b on a. And then original y was equal to a y dash. And so when you rearrange it to make y the subject, the new rule that you get is 1 on a f of x dash minus b on a. So this is the rule. This is the rule that we want for what type of transformation? For this transformation, the ax plus b and then y on a. That right here, this is what this means. Okay, don't confuse it with what I was trying to say before. Don't confuse that when we say f of 2x plus 1, we're not doing this. We're not saying f of x plus 1. If I take off that 2, I'm not saying that this means this usually means left 1. This here actually means right 1. That's the difference between the two. Okay, so one is actually looking at the rule and one is actually looking at what I want, the transformation that I want. Okay, so hopefully that clarifies that misunderstanding that I may have not addressed in class. So in a nutshell, what I'm trying to say is when you're looking at these problems and they give you a random variable x and then they ask you, say, so 2x plus 3, you can actually just read that directly from itself. So you can already say that this means that you will have 2x plus 3, and then that means it's y divided by 2. Because whenever you dilate to the x, you have to dilate to the y to compensate for that change in area. So this actually means right by 3, and that actually means dilation of factor 2 from the y-axis, whilst this is dilation of factor 1 on a from the x-axis. Okay, so you literally read this part of the transformation. Okay, so when we say this, that's what I'm referring to. Hopefully that clarifies that bit, and if you wanted to write the notes, I already got it in the notes here for you, that those are the transformations. Cool? Let's do one example. So that's the theory that I think I didn't nail down too well in class. So let's do an example, something very similar to before. Yeah. This time I'm going to use a CAS instead of actually doing it by hand. You can do it by hand to solve this, but let's do it on CAS. So first one, you've got a probability density function for g of x. So g of x is some function. Yeah. So there's g of x. I know it's a probability density function, so the area must equal to 1. To do that, well, I know everywhere else is 0, so it's 0 and 0. It's between -2 and 2, so maybe I should have drawn it like this. Actually, I should have drawn it like this. So -2 to 2, the area is equal to 1. So how do you solve for it? Well, type in your CAS, integration, so the area under the curve between -2 to 2 of g of x dx, it should equal to 1, and solve that for k. All right, so I'm going to get my CAS out. This is something else. Let's do it. Define g of x is equal to, what do we have? We have k times 4 minus x squared. And it's between -2 and 2. Okay, so control given Hiya. Computer's a bit laggy. Given it is between, I'm just going to put in the inequality signs. It's between negative 2x and 2. Is that right? Yep. And I'm going to try to solve for menu 3, 1. Solve for g of x to equal to, not g of x, the integration, the area under the curve between negative 2 and 2 of g of x dx to equal to 1. So I want the area to sum up to 1, find k, right? So k is 3 on 32. All right, cool. So we got k now, 3 on 32. Okay, you can do the integration if you wanted to, or by hand or by cas. So now we got k. So I'm just going to go back and change k. So k is currently now 3 over 32. Okay, so that means that if I find the integration from negative 2 to 2 of g of x dx, it should equal to 1. Great. Next one, describe the transformation that maps this g of x, and this is what I want. So I want 3x plus 2. So I want to triple all the random x variables, and then I add 2. So in a nutshell, so let's draw that picture again. From negative 2 to 2, whatever the g of x is, doesn't matter, right? So let's say there's 2 points there. I know that I want this coordinate, okay? This coordinate when x equals negative 2. We don't know. Oh, we can find the y value. So we just sub negative 2 in and we'll know what. Okay, let me just work it out. G of negative 2 and G of 2. Oh, it turns out it's the intercepts. Okay, so let's say that was from there. I don't know, G of x kind of like that. And it comes back, right? So you got 2, 0 and negative 2, 0. What we're saying is when the x coordinate, the coordinates are negative 2, 0, okay, I'm saying for every xy coordinate, I want this transformation. I want 3x plus 2, and then remember it has to be y divided by dilation. So the new coordinates would end up being 3 times negative 2, which is negative 6, and then plus 2, and this one would be 0 divided by 3. So it ends up being, what, negative 4, 0. So my new coordinates, after you triple it and you add 2 to the x, it is now going to end up at negative 4. So say over here. So negative 4, 0. After doing all that, right? So I'm going to go to the right by 2, and I'm going to dilate it by a factor of 3. So that's where it's gone. Yeah? Then the next one is you've got 2, 0. So the coordinate's 2, 0. I follow the same pattern. So triple x, so triple of 2 is 6 plus 2, and then y 0 over 3. And that gives you now 8. 0. So that this point now has been dilated to 8. Let's just say 8 is over there. So 8, 0. So the graph has obviously gone some sort of wider. So who knows? It may look like this. It may look like that, something like that. I have no idea. Okay, I'm just making it up right now. So in fact, I just realized the original function was a parabola. So it was probably like this. Okay. Now, we know the domain has changed from negative 2 to 2, and now it's gone from negative 2 to 2 to negative 4, 8. So the domain of this new function is negative 4 to 8. But we could have done it another way as well, which is the way I did it in class. You see, we could have used the transformation like I just did just now, or you could have done the way I did it in class where I said, well, the original domain was from negative 2 to 2. The transformation that I'm applying is, now remember this transforms to, remember the rule, it was f of ax plus b is equal to 1 on a times f of x minus b over 2. Oh, not over 2, over a. Okay? And so with that concept, I know now, well, instead of x, what's my new transformation? It will now be x minus 2 over 3. Well, you can rearrange that if you like to think of it. You can rearrange it. I'll just follow the rule that I've just given to you guys there. But if you rearrange that, it's x minus 2 over 3, and this is negative 2 to 2. So you can see, again, times everything by 3, and you get negative 6 less than or equal to x minus 2 less than or equal to 6, and then add 2 on both sides. And you realize with the transformation, what do I get? Same thing. Okay, so this is what I did in class, and just being careful with this bit. okay, because we know this is what I want, and this is the transformation rule. Okay, so this tells me what I want. It's the actual rule. This one is the actual rule that you type in. Okay, so your function will follow whatever this is. This is the new function. That's the rule. Remember the proof that I showed you here. This will tell you the transformation rule. Okay, and maybe that's where it was confusing in the notes. So when they say describe the transformation, really, you can look at this and say, well, that's just a dilation of factor 3 from y-axis. So it means it's a horizontal stretch. This is to the right by 2. Okay, and don't forget you also have a dilation of factor 1 on 3 from the x. So it's a vertical compression just to compensate for that area change. Okay, but those are your 3 transformations there. It's dilation, right, and then dilation again, which is what these 3 represent. And then find the domain and range. Well, we just found the domain as I was describing what it is. And the range, well, you can find that by sketching the function. So you know that it was g 1/3 of g of, what was it again, x minus 2 on 3. Type that, and that's your new function. So here we go. Let's go back to our CAS. I'm going to define, I'm going to do, let's call it h of x. Actually, no. Let's do, so I want 1/3 of g of x, what was it again? Minus 2 over 3. That is the function I want. Okay, ooh, that looks nasty. Maybe I shouldn't have put the intervals in. But hey, at least they got the domain for me there. Maybe I can do complete the square of this. Does that work? I just wanted a nicer looking function. No, it couldn't do it for me. Maybe I'll take off the domain. I'm going to do this again, and then I'm going to do this again, and then I'm going to complete the square of this, just so I get a better looking function. There we go. So that now tells me this is equivalent to if you had subbed it all in into the equation. So remember, it was g of x is equal to 3 over 32 of 4 minus x squared, right? Then all you're doing now is you're literally substituting this into this and timesing the 1/3 at the front. Okay? And if you do that, this will give you the equation 1/8 minus x minus, what's that, 2 squared over 288. And I like this form better just because I knew it was a quadratic. It's easier to read the graph, so I can clearly see the turning point is moving to the right by 2, which we knew, but then this is up by 1/8. So I know the turning point must be at 2, 1/8. So what's the range? The range clearly is from 0 to 1/8. But alternatively, you could have done what we did in class, find the derivative of the function, and then let it equal to 0, find the stationary point, and you would have been able to figure out 2 and 1/8 as well. But because it's quadratic, it was easier to just do complete the square on the CAS. All right. Or alternatively, again, you can sketch it. So, no, that's something else. Let's delete. Ooh, what did I do there? Oh, no. I changed it. No, 3 function. Okay, we're back. Let's delete this. Let's delete this. So f of x. Wait, what's going on? Delete that. So this, oh no, that's not f of x. Was it g of x? Oh, g of x. That's right. Here's your quadratic. But remember, we wanted it from -2 to 2. So I probably will need to put a restriction. So from -2, whoops, -2. I'm too lazy. I'm just going to do it like this now. So there we go. That's the graph. And then we had the second one, which is 1/3. Ah, no. 1/3 times g of x. No, it was g of x minus 2 and 3 from memory. Oh, wow, that doesn't look good. All right, maybe we need to fix the domain. I'm doing a bit of a cheat. Oh, that doesn't look good. Okay, let's try to make it look better. Menu for 2, zoom box. Let's do it somewhere around there. Let's see. What does that look like? Okay, that looks better, but I've totally missed the intercept. So menu for 1. It's all exact values. I should have chosen, what was the intercepts again? I'm just going to cheat. All right, there we go. It's over there. Okay, it's right here. Let's make it a bit better. Menu for 2. And let's do this. I'm obviously doing a bit of a rush here because I'm trying to get to a point that you understand what I'm trying to say here. But here we go. Here's your graph. And we can see that the maximum for the new transformation graph is somewhere over here. And we know it should have been 2 1/8. There we go, 2 1/8. So that was another way to find the range as well. So we found the domain was meant to be -4 to 8. And then, oh yeah, that was the domain. Forgot about that. -4 to 8. And then the maximum is 0 to 1/8 over there. Okay. So answering that question, find the domain and range. It's pretty straightforward once you know how to find the function. So recapping again, so we knew what we wanted was the ax plus b. That's what we want. Okay, so ax plus b was 3x minus 2, was it? Was it minus 2 or plus 2? Plus 2. That's the transformation. Okay, that's what we want. The equation to find out what that is, so from g of x, what is the new rule for it? It was 1/3 g of x minus 2 on 3, which turns out to be, it was 1/8 minus, I think it was x to the right by 2 over 288, something like that. Okay, so that's the rule for the new transformation equation. From that, you can sketch this and find the maximum, or find the stationary point and find the maximum, or do what I did. I just read the turning point from this quadratic, and hence I was able to find the range and the domain. Then they say the last bit, let y equal to 3x plus 2. So they're just giving another variable, and they're just saying, find the rule. Okay, so we had the rule for g of x. Now, what if I want g of y? What does that look like? Okay, well, we already got the equation. It was 1/8 minus, what, x minus 2 squared on 288. And that was between, for the domain, was from -4 to 8, and it's 0 everywhere else. There you go. And that's your answer. Now, I know that looks a bit messy, but hopefully you're seeing what I'm doing here. There's a difference between what I want, okay, for the random variable x, what I'm doing to it, and then what is my actual transformation equation. Hopefully that clarifies what we did in class, okay? You can have a go with this one. It's the same idea. I'll write up the solutions and you can have a look in OneNote. It's just all underneath all the previous notes that we did. Okay, so this video is just to supplement what I felt that didn't do too well. You can have a go with this one. This one should be a bit easier than the one I just did, but that's another example. Okay.